In this video, we will look at an implementation of binary tree in C++. So we will see a class that represents binary trees in C++, and we will implement a few member functions that compute things like the height of the tree, the size of the tree, and uh, preorder traversal. And we also talk about the other two uh, traversal algorithms that we covered in the previous video. So first, let's start by taking a look at the class itself. So in terms of the member variables of this class. So first of all, I'm using templates here so that my binary trees are capable of containing data of different types. So T is going to be the type of the data or the key that I put in the binary tree. And when I create these binary trees, when I declare an object of this class, then T will be replaced by an actual type like int, char, string, and so on. So that's the reason that we have this template type name T here. And then we have a class called binary tree. And at the moment, let's focus first on the member variable. So inside the private section, similar to linked list, if you look at the video for linked list, we did something similar. We define a class that represents the nodes of a tree here, right? And if you remember, a tree node contains some data of type T. And in the previous videos, we talked about this, that we need two pointers. So two tree variables of type tree node star called left and right. One of them is a pointer that points to the left child, and the other one is a pointer that points to the right child of this particular node. So every node contains some data. Every node object, or I should say every tree node object, contains some data of type T, whatever T is. And then it contains also two pointers. One of those pointers stores the address of the left child of the node, and the other pointer contains the address of the right child of the node. Okay, and I also included a constructor for this class with one parameter, d. And what this when its constructor is called, what it does is that it creates a tree node object where the data is initialized to d, and left and right pointers are both null pointers. So this is the only constructor I'm defining for this class called tree node. And remember, if the left pointer is null, it means that the node doesn't have a left child. If the right pointer is null, it means that the node doesn't have a right child. And if both of them are null, it means that the node doesn't have any children, which, if you remember in a binary tree, these kind of nodes are called leaves, right? So if both left and right are null, then we are dealing with a leaf node. So that's the class here, the class tree node. Now, this is not a member of the class. This is just this is not a member of the binary tree class. It's just the definition of another class. The only member variable that we have in this class called binary tree is down here, tree node star root. So root, which is a pointer that stores the address of the root node of the binary tree, is the only member variable that we have. Similar to, again, linked list, where you had the head pointer, and that was enough to explore the entire linked list. Knowing the address of the root node in this pointer variable called root is enough, because from the root, you can use the left and right pointers to find the left and right children. And from each one of those, we can use their own left and right pointers to find their left and right children, and so on. So the only information that I need to be able to explore a binary tree object is the address of its root node. Hence, we have only one member variable. Now, the rest of what's going on here is for convenience. So I've defined a function, or actually, I should say two functions that we can call to build uh, binary trees. One of them is called build random, and the other one is build. In the build random, you just specify the size, and it generates a binary tree of that size, but the shape and the keys or data in that tree are going to be chosen randomly. But the other one, you specify the size, and then you provide the, let's say when you call this build function, you say 5 here for the size, and then you have to provide through the keyboard 5 values for the keys or the data that goes into the 5 nodes of the binary tree. And then the display function shows how uh, the, the binary tree created looks like. Now, these are not the focus of this video. As I said, the focus is on other member functions like preorder and height, post order, in order, and maybe the size. Okay, so let's start with a simple one called, let's start with the size. So it's going to be a function that returns the size of a binary tree. Remember, the size of a binary tree is the number of nodes in the binary tree. So it returns an integer, and it's called size, like this. And I can make it a constant function. Remember, this constant at the end means that this function doesn't change anything about the object that calls it, but it's not necessary. Okay, now what we need to do, for a reason that will be clear in a moment, I need to define a helper function that is not going to be called directly from the outside of the class, so it can be private. But this one is the actual function that computes the size. Um, and this one, unlike the public one, requires a parameter, which is a tree-node star parameter. Now, when I implement this function, it makes more sense why we need this. Okay, so let's implement these two functions now. So I have two functions to implement. So here's my build random function, very simple. And here's the other build function. You see that it uses tin to read the different keys from the keyboard. And the display function is here. And it requires two helper functions, display left and right. And here we are now implementing the size function. Okay, since I'm using template, I should say template type name t, and it's an integer, the return type, binary tree of type t, and then double colon for the scope operator, and then the name of the function is size. Let's start with the private one, which is the more interesting one. It has a parameter called tree-node star PTR. Okay. Now, as you will see, similar to height, this is going to be a recursive function, and I need the address of the current node to be able to make recursive call. Okay. So if the base case, if PTR is null, now imagine that in the first call, PTR is going to be the address of the root node. Now, if the root node is null, it means that it doesn't have a left or right. It doesn't have left or I'm sorry, PTR is the pointer that points to the root node. So if PTR is null, it means that there is no root node, right? So because remember, root is the pointer that points to the top node in the binary tree, and if that pointer is null, it means that there is no point. There is no node on the top of the tree, which means there is no node whatsoever, which means that the size is 0. The tree doesn't have any nodes, right? Remember when we talked about trees a couple of videos ago, we said that the simplest kind of tree that you can imagine is a tree with no nodes whatsoever. So in that case, um, the tree is an empty tree, and the size, the number of nodes is 0. Okay, that was easy. That's the base case. Otherwise, so now otherwise means PTR is not null, which means that it is actually pointing to a node. So we have at least one node, right? So, and you remember we are counting the number of nodes, right? So I should return 1 plus. So 1 is the current node that PTR is pointing to. Now, the node that PTR points to might have left and right children, and those two children may have their own children and so on. So I have to count those as well. Now, here's where I make the recursive call. I call this function size again on the left child of the node that PTR points to. So I can say PTR arrow left. So this call to size says, okay, instead of looking at the node that PTR points to, go to the left child of that and do the same thing. Make a recursive call to count all the nodes on the left branch or the left subtree of the node that PTR points to. And then I do the same. I make my second recursive call, this time PTR arrow right. So this second call is going to count the number of nodes on the right subtree of the current node. And there you have it. That's your size function. So the base case is if PTR is null, you don't have any nodes because PTR is supposed to point to the root initially. In that case, you return 0 because you don't have nodes. If it's not null, then there's at least one node. So that's the 1 at the beginning. And then the current node is the one that PTR it points to. Now I need to know how many nodes are on the left and right subtrees. And that's why I make these two recursive. Now, this is the private function. And first of all, you see why I need the parameter, right? Because I have to tell my recursive call to go to the left or right subtrees and make your recursive call. So that's why I needed the parameter. But when the user calls the size function, they created binary tree object, say T1, and then they want to say T1.size without any parameters. Give me the number of nodes in T1, right? That's why we have this other function that is the interface. That's the one that the user uses, right? Now, the implementation of that is very simple. So template, type name T, int binary tree of type T, the scope operator size again, but this time with no parameters. So this is the public function. And the only thing that this function does is that it calls the other size function and guess where it should start counting the nodes. If you want to know the number of nodes in the entire tree, where do you think we should start from? Obviously the root node, right? So it calls that recursive function size from the root, and then it starts, making these recursive calls. If the root node is empty, then it returns 0. Otherwise, it says, okay, 1, so that's for the root, and it goes to root arrow left and root arrow right. So the left and right children of the root, and for each one of them, it repeats the same process. And by the magic of recursion, it counts all the nodes in the tree. Now, I encourage you to draw an actual tree and, small size, maybe 3, 4 nodes, and walk through the steps of recursion to make sure that you understand how this works. So there we go. Now we have the size function. Okay, so for example, in my stores, when I create a random tree with 7 nodes, and then I can display it. And then to make sure that I've done everything right, I can say cout t1.size. And if the size function is implemented correctly and the build random function is implemented correctly, obviously you should get 7 here because that was what build random was supposed to do. Okay, so that's one member function. Another member function that I want to show you, and eventually after seeing a couple of these functions, it makes more sense. So the next one, which is kind of similar, is the height function. If you don't remember the definition of the height function in the binary tree, you can go through the previous video when we defined this. And it's a similar setup where there is a public function in height with no parameters. So that's the interface. That's the one that the users call to find the height of the tree. And then there is a private one with one parameter that is the address of a tree node, so a tree node star. And that's the one that is actually recursive and goes to the left and right subtrees and so on. Okay, so similar to size in terms of the setup, which is, again, you see that it's kind of similar to for the build function and display function. For each one of them, we have this kind of situation. Okay, so let's do it now. So we have template, type name, T, int is the return type. The name of the class is binary tree. Since we use templates, I have to put the bracket T here. And then the scope operator, double colon. The name of the function is height. And then again, let's start with the one that is actually doing the computation, the one that is the private version of the height function with one parameter, which is a tree node star. Let's call that PTR. Okay, so the idea is that, again, initially PTR is going to be the address of the root node. So we start from the root and we try to compute the height of the tree recursively. Now, if you remember, the base case, now here the base case is a little bit tricky. So if PTR is equal to null, then we return -1. In a moment, it will be clear why -1 and not 0. Okay, but yeah, -1 for an empty tree, a tree without any nodes. Not to be confused with a tree that has only a root node. For that, the height is 0. This is a tree with no node whatsoever, not even a root node. So you just have the root pointer that doesn't point anywhere, and in that case, you return negative. Okay, otherwise. Now, otherwise means the pointer PTR, which is initially the root pointer, is not null. So we have that root node. Now we need to look at the left and right children and see what is the height of the left subtree and the height of the right subtree. So those are my two recursive calls similar to size. So the first call is to size on PTR arrow left returns an integer. I'm going to store that integer in an integer variable called left height. And then another one, RH, again, a recursive call, not to size, sorry. We are computing height. So the recursive call is to height. Similarly here, a recursive call to height, this time for the right subtree, so PTR right. That one also returns an integer, and I'm storing that integer in a variable called RH, the right height. Okay, now the height of the total tree is the maximum between these two plus 1. So return, or I can say if LH, the height of the left subtree, is greater than RH, then we return LH plus 1. Otherwise, we return RH plus 1. Okay? Now, why the return value for the case where the tree is empty is not 0, it's -1, and why this finding maximum plus 1, I need the whiteboard to tell you why that is. So let's pause here and go to the whiteboard. Okay. Let's start with why we compute the height of left and right subtrees and then take the maximum between the two and plus 1. Where does that come from? Okay, so let's say this is the root node. So there's a pointer here called root. You remember the implementation that points to this node. And potentially this can have left and right children, not necessarily, but it could be. And then each one of them may or may not have left or right children. Let's say this one has left and right children, but this one doesn't. Or let's say it does. Okay, so let's say this one also has left and right children, and this one has a left child. And let's say that's it. Okay, so this is the root node, and this is where PTR starts from. Now, what we said was that if PTR is null, return -1. That's something that I will talk about a little bit later. But if it's not, which is in this case, so there is a root node, then we said make recursive calls on PTR arrow left and PTR arrow right. Now, PTR arrow left is going to be here. So this is PTR arrow left. And this is PTR arrow right. Okay, the address of this node and this node. Now, when I make this recursive call, these recursive calls, basically what I'm saying is that compute the height of this tree and also compute the height of this tree. Left and right subtree. Okay, so when I say height of PTR arrow right, that's a recursive call that computes the height of this tree and returns it. And when I say call height on PTR arrow left, basically what it means is to compute the height of this tree here the left subtree, and return it. Okay, so this is what we call LH, and this is what we call RH. Now, according to this picture, for this particular example, the height of this tree, remember the height is from the root. What is the number of edges in the longest path from the root to a leaf? Now, in this is simple enough that you can guess that there is 1, 2, and this is the longest path from the root to a leaf, because the other leaf is this one, and that there is only one edge here. So this is 2. The height of the left subtree is 2. The height of the right subtree from the root, which is this node here, to the 2 leaves, each one of them is 1 edge only. So the height is 1 in this case. So the 2 recursive calls return 2 and 1. The question is, from 2 and 1, from the results of the 2 recursive calls, how can we compute the height of the entire tree? And if you think about it, the height of this entire tree, if I change color here, the height of the entire tree is going to be the longest path from the root to a leaf is the path that goes here, here, and here. So the height of the entire tree is 3. And that is because between these two, this one has the higher value for the height. So it takes 2 edges to get from the furthest root, furthest leaf to this node here, 2 edges, and then 1 extra edge to get from here to the actual root, right? So first we need to take the maximum of these 2 because this one is longer, and then add to that 2 plus 1 because of this extra edge. So we take the maximum of LH and RH, that's the G, H. So we take the maximum of RH and LH, the result of the 2 recursive calls. So the maximum of 1 and 2, that's 2. And then to consider this extra edge to get to the actual root, I have to add 1 to that. Okay, and that's exactly what we did with an if-else statement in the implementation, right? So that's the rationale for that. The other thing that I promised you to explain is why for an empty tree, we set the height of the base case to -1, and that's 0. And the reason for that is, if you remember, the simple cases for a tree, this is a tree with 2 nodes. The height here from the root to the leaf, there is only 1 edge, so the height is 1. If we have only 1 node with no other node, so a tree with only 1 node, here the height is going to be 0 because this is the root node, this is the only node, this is also the leaf node, and that the path from this node, which is the root, to the leaf, which is itself, is a path with no edges, so 0 is the height. Now, if we have the empty tree, so here size is 2, here size is 1. Now, if the size is 0, which means a tree with no node, so you just have a pointer that is null, that doesn't point to any node at all, the height should not be 0 anymore. It should be -1. And that is because, remember how the recursion works, right? In this case, if we do the recursion, we have this, let me change color again. We have this pointer, PTR or root, pointing here, right? So root or PTR at the beginning is not null, right? And when it's not null, it makes 2 recursive calls to the left and right subtree. But what is the left subtree here? The left subtree is empty. What is the right subtree? The right subtree is also empty. Okay, so we call height on an empty tree here and an empty tree here. We take the maximum of those 2 amounts, so that will be the height of this empty tree, right? Because that's what we have at the left and right children. And then we add 1 to that. So when we add 1 to that, we are supposed to get 0. So those 2 heights that we get from these 2 empty trees must be -1, so that when we add 1, according to this formula here, right, 1 plus, we get 1 plus -1, 0. So that's one way to justify why in the base case, in this case, the height is -1. Because we need this case, when the size is 1, we need the height to be 0. Okay. Now, the final thing that I want to do in this video is to implement the tree traversal algorithms. One of them and the other two will be similar. So let's do pre-order. Okay, so where are we? Here we go. Oh, did I forget to do the public height? Yes. So similar to size, I need um, int binary tree of type t height. This is the public version of the height function, and this is the one that the user will be calling. And the only thing that this function does is that it calls the other height function, the helper function, on the root node. So start from the root, do your recursions, return the integer at the end, and that's what I'm going to return as well. So this is just the interface. Okay, now pre-order, there will be again a public and a private version. So pre-order, that's the public one with no parameter. I'm making it a void functions, and my intention is that this pre-order traversal prints the values or the keys in the binary tree in the when it does the pre-order traversal on the console. But it could be that it puts them in some kind of container, like a vector or an array, and returns that in that case, it may not be void, but it's based on the same kind of idea. Now, here's the private version reorder. And this one again requires a tree node star parameter. Okay, so the implementation is going to be very simple and very similar to um, the, the one that we did on the board in the previous video. Almost identical. Okay, so template type name team, and then it's a void function. The name of the class is binary tree, template, and then pre-order, tree node star, PTR. There we go. Now, remember, pre-order first processes uh, the current node, then it makes a recursive call to the left and recursive call to the right. Um, and the base case is when your binary tree is empty. In that case, pre-order doesn't do anything. So I say if PTR is not equal to null, do the following. Okay, so see out PTR arrow data, and then maybe put a space after to separate them, and then make a recursive call, pre-order, on PTR arrow left, go to left subtree and do your job. Then pre-order on PTR arrow right. So very similar to what we did on the board, except that we use dot here. We're using arrow because that's the uh, syntax in C++ for accessing members of a class from a pointer. Okay. Now, what happens to the base case here? The base case is implicit. The base case is when PTR is equal to null. So the condition of the if statement in that case is going to be false, which means that it's going to skip the if block and there isn't anything left, so it's just going to return. So we can imagine that the base case is this, else don't do anything, but we don't need that because that's just extra code without any effect, right? So the base case is implicit. If PTR is null, your binary tree is empty, stop, don't do anything, okay? And the private version, template, type name T, void, name of the class, type T, double colon, pre-order. This one doesn't have any parameters. And this is the one that the user is going to call by saying a T1.preorder. And the only thing that this one does is calling the other pre-order function and giving it the address of the root node. That's it. Okay. Now, for in order, it's going to be very similar, except that you put the cout statement in between your recursive call. Obviously, your recursive calls are going to be calls to in order, right? And for post order, again, Similar idea, except that you put the out statement after the two recursive calls to left and right subtrees. You see out the current uh, data, right? And obviously, the calls will be to post-loading. Now, if you want to challenge yourself with similar kind of functions to practice this, here are a couple of functions that you could implement, and they follow the similar logic with two versions, public, private, and so on. One of them is a function that counts the number of leaves in a tree. Like it says, this binary tree has 2 leaves, 5 leaves, whatever. The other one can return the list of all the leaves, right? The data in every leaf put in a vector or a list and is returned. Or maybe it prints the data in all the leaves on the console. The other one is the leftmost node in a binary tree. Now, in a binary tree, the leftmost node is is found this way. You start from the root node, and check to see whether it has a left child. If it does, you go there and check to see if that node has a left child. And if it does, you go there and so on until you reach a node that doesn't have a left child anymore. And that is the leftmost node by definition in a binary tree. Now, again, by using recursion, you can implement this as well. And these are all nice exercises for practicing defining recursive functions on binary trees.